Last class, we made it all the way through. 34 worksheets, something like that. 11, 12. Now I think it was like 13 homework assignments and WebAssign, bunch of reading quizzes, and all coming to a close here. Actually, next week is when it comes to a close. I want to share my Google Chrome screen with you real quick. Show you what the registrar has in store for us. And I didn't do it. Wouldn't have been my choice. I'd have gone earlier in the week. But I guess to spread it out, that's our final exam period. If we were meeting in Dunning Hall, you'd come into our classroom at 9 o'clock. You'd have 2.5 hours to take the exam, be finished up at 11:30 a.m. on Thursday. So instead, much like the midterms, what I'll do is Wednesday around midday, so that you have about 24 hours to work on it, I'll post into Canvas and on WebAssign 2 parts to a final exam. Very similar to both midterms. I don't think you'll need the full 2.5 hours to work it, but give yourself enough time so that you can have everything uploaded. The part A that'll be worked out like worksheet problems uploaded by 11:30 on Thursday, and you'll be able to get your solutions into WebAssign for that portion of the exam. I want to flip over here in Google Chrome just to talk about something. And I don't think it's going to be an issue here. I've got no indication that it's a problem, but I have to tell you, in the short time I've been working here at Washington College, I spent too much time talking to Dr. Crockmall. So I just want to make sure that everybody understands the rules and why on the rules, and the honor aspect of taking an exam, because it is an exam, and it will focus on the material since the last exam. This is the second midterm here, which went right up to Heisenberg's uncertainty principle. Okay, and I think that was worksheet 23. And so the focus of the final exam will be worksheet 24 to the worksheet we're going to do today, which is worksheet 34, which is very short. And by the way, like I've done in the past, I'll post in a PDF document my solutions to all those worksheets. But remember, it's all the Schrodinger wave equation stuff, one-dimensional problems, the infinite square well, the finite square well, the tunneling problems. And by the way, only one person attempted the extra credit. There's still, I forget what day I had it due, but I haven't graded that one yet. So if you're still thinking about getting that extra credit, it's still up there. And I haven't graded the one person. I haven't even looked at the one person who put it in, but I open it up. It's just an algebra drill. It's a lot of algebra, as that person will tell you. Any event, back to what we're talking about here. Open book, and hopefully you'll see these were the rules from the last midterm. They haven't changed. Open book. There is an equation sheet, and that just keeps you from having to page and waste time going back and forth through your textbook, which is digital, I assume, for most of you. You got to do your own work. Okay, you can't consult with any of your colleagues in class here or anybody outside of class who might have expertise in modern physics, and any digital persons. And that, there's that Chegg system expert I came to find out about last semester. You can't do that, obviously. And I hope everybody would realize that. There were actually people who went to their honor award saying, well, I didn't know this was illegal. Okay, you said we can use some websites. And if somebody else does the problem for you and you copy it and you put it on a final exam paper, I would hope most people would realize that's cheating. Okay, I should tell you how the people in last semester got caught with the Chegg expert solutions on the final exam. The expert, and I put quotation marks around the expert because it was almost laughable what this expert did. It was a distributive property thing. There were 2 terms inside of parentheses with a math expression. I think it was like an X outside of it. He just didn't distribute the X over both terms inside the parentheses. And 4 people copied that exact same wrong answer. And so it was, I couldn't say I didn't see that. Obviously, I saw the issue. Okay, so don't do that. And I will say this, this is a class that it forms kind of the foundation of things you're going to do in the future. right? Number of you taking the advanced electricity and magnetism course next semester. The math techniques that I'm showing you here, that I get it. You might not be able to just repeat it right now, but you're going to see them again next semester. If you take the quantum mechanics class when you're seniors, you'll see these things again then. Even in the advanced mechanics class uses a lot of the differential equations techniques that I'm showing you. And so the only person you're cheating if you get somebody else to solve the problem for you is yourself, because down the road it's going to catch up to you. So don't do that. Okay. Your work must be your own. Don't consult with any other people. You can use resources that are listed in bullet 3 there. Okay, your textbook, obviously, your class notes, and anything that I posted on Canvas, and that'll include my solutions to the worksheets that aren't posted yet. Okay, and which will be the bulk of the material here. You can certainly use those things as a template, but that's about it. Okay, and it's not like I'm going to ask some completely different questions. So my Canvas solutions to the worksheets, I think, would be pretty important to you. In your textbook are a bunch of solved example problems, which I think are pretty important for you. And part of learning physics, I think, is to see the patterns in these things. Okay, what websites can you use? And that's addressed in bullet point 4 here. And I want to make sure we're clear on this too. I know I have, it's an older one, but I have a kind of advanced Texas Instrument calculator. The current version, I think, is called the TI Inspire. And I know those things are fairly expensive. If you've got one, that is great. It'll be a great tool for any science discipline you go on to major in. It does things that a standard calculator doesn't do. It actually will solve a derivative for you in symbolic form. It'll take an integral for you in symbolic form. It'll solve two equations and two unknowns for you symbolically. Okay. People have the paradigm for calculators is it'll just do math for you. It'll multiply numbers and divide numbers and take square roots and take trig functions and give you the answer for a trig function of an angle, that sort of thing. No, the calculators have stepped it up a notch. They'll actually do calculus for you. They'll do algebra for you symbolically. But not everybody can afford a $200, $250 TI Inspire or equivalent. And so that's the reason I'm making an exception that you can use the online calculator apps on your work. Okay, so just tell me if you're doing it. You need to do an integral, and you did it either on a TI Inspire or you went to Wolfram Alpha, who I said I don't like as much anymore because they're getting greedy. A lot of some of the problems I've started to do, I'm timing out, and you need to join and pay for the pro version in order to use it. MathNet's out there. What was the other one? Sam, you had one of these that you were using that worked pretty well, and I've forgotten the name of it already.
It's just integral dash calculator or Simba Lab's another one.
Symbolab was the one I was thinking about, but yeah, just an integral calculator. And so those are legal. Any of those sites, even if I found an app one time that'll just solve a quadratic equation for you. Literally, you don't have to know the quadratic formula. Those are legal. Okay, going to a place like Chegg, where you're going to possibly find the solution or have a system expert solve the solution for you, or someplace else where the solution manual, the instructor solution manual for our textbook, Thornton and Rex, is somehow posted because some industrious graduate student at some university in the country posted all the solutions up, and you just go in and Google the solution. Oh, that's not legal, and that's not what we're doing. We're not the mathematicians here. We care about the physics, but you just need to tell me how you did your integral, because there's very likely going to be an integral. I mean, you have to do an integral in order to normalize a wave function, for example. You need to do an integral in order to find a probability of finding a particle in a particular location. So it's likely you're going to have to do an integral. You might have to take a derivative. If you use one of these mathematical tools to do it, just tell me hey, I use MathNet or I use Symbolab or whatever in order to do this integral. Here's the result I got. I put this in, this is the result I got. And that's all you need to do. Okay. Same thing if you use a TI Inspired, make sure that I know what you're doing right there. Okay. Chegg, any website like it where somebody's posting the specific problem that I picked and assigned on the exam, well, if you go there, you're cheating. And again, the person you're cheating most is yourself. Because, unlike humanities classes, where it often doesn't matter whether you take Shakespeare 1 or Shakespeare 2 first. Physics and most science disciplines, we build, okay, from the bottom up. And so if for some reason you didn't quite get a skill in the bottom of the pyramid, it's going to be a lot harder for you down the road when you take another class. All right, the times here are wrong, but you got to complete part A, which will be a couple problems like a worksheet by 11:30 a.m. Okay, on the Thursday of exam week when the normal exam would be over, and part B in web assigned exactly the same thing. Okay. And I don't think, as I said, it'll take you the full 2.5 hours, but please give yourself enough time so that you're able to get a great grade. Everybody's doing pretty well in here. I hope to be able to grade on a kind of a graduate school scale, because if some of you are considering graduate school, that's how your transcript's going to be viewed, right? Hopefully you understand that if you do go on to graduate study in almost any discipline, a C is a failing grade. Okay, that's my last day of class kind of advice for you. In a master's program or a PhD program, you can get A's, you can get A minuses, you can get B pluses, you can get B's, even a B minus or two, but 1C, you might be able to survive. You get a second C in a graduate program, and you're going to be asked not to renew in that program. Okay. And if that means you're getting a stipend or something like that to pay your living expenses and your tuition, that will be withdrawn by the school who's offered it to you. So everybody's got an A or a B right now. I want to keep it that way. And I'm willing to give all A's out if everybody does really well here. Okay. So that's the exam. Any questions on when it's due? I am going to be leaving town shortly after to visit my son for Christmas. We'll be back way before Christmas, but there's really no grace period for you because I'm getting out of town later on Thursday. Okay, so that's the deal. All right, on to the last bit of material for the course. I'll stop sharing this with you and move on and let you see my iPad via this great AirPlay link here, which hopefully is working. It was working this morning. Yes, it is. And I think I want to start with this slide right here. And at the very top there is Schrodinger's wave equation in 3 dimensions. And if you notice, I've been working on this problem now. This is the 4th class in a row. And that is the way physics upper level classes kind of go. We've been doing the hydrogen atom, and it has 3 aspects. This is now the 4th day, and I'm finally going to look at the end of it. We did 2 before the Thanksgiving break. Talked about the angular solution on Monday, and now we're going to delve into the radial solution. I want to review back what we did. We started with Schrodinger's wave equation that I wrote up there in the top in 3 dimensions, not just the one-dimensional case like the infinite square well or the finite square well or the barrier problem. I put in spherical coordinates what the Laplacian is. And I had to go look it up. Certainly not something I know. Okay. Just check something here. Yeah, I am recording. Good. And then we did a technique, which a lot of you will see again very soon next semester in the advanced electricity and magnetism class. And that is this thing called separation of variables, where we assume that the solution to that 3-dimensional, in this case spherical 3-dimension coordinate system, we assume that the solution is separable into 3 separate functions, each only a function of their own variable. It's good hope. We did some math on it, and we wound up looking at these 2 equations right here. And today we're going to focus on the radial equation. By the way, the angular equation, we said the solutions were solved by a guy named Legendre, called the associated Legendre equation and associated Legendre polynomials. Today, we're going to have an equation called Laguerre's differential equation, and the solutions are something called Laguerre functions, and we'll show those here in a second. Remember how we got here. That's the mile-high view right there. That's the overview. Okay, we assuming that we had a separable solution, we looked at what the derivatives were. Okay, and that's what I have right. Stop it. That's what I have right here. What the various derivatives were that were necessary. I plugged them in to Schrodinger's wave equation. I multiplied in order to isolate this term right here. I multiplied by the denominator and divided through by the full wave function. Okay, and moved this term to the other side of the equation, and you can see it showed up right there. And we made the mathematical postulate that the only solutions that will work for this equation are a constant, or are constants. Okay, and we called that particular constant, for reasons that came up later, minus m sub l squared. By the way, unfortunately, you're gonna have to wait till you take quantum mechanics to know why L. And the answer is it's related to angular momentum. And I'll just tell you that right now. That's why we picked L of all the letters. And you saw when we went on in the in the associated Legendre polynomials, L was one of the separation constants as well, and it's because it is associated with angular momentum. That's why L, as opposed to any other letter. In any event, it's just a constant though, and we looked at these two terms right there, and we said, okay, the solution to that guy is G is equal to a complex exponential. And we allow m sub l, we showed it had to be an integer so that the function is single valued at 0 and 2 pi, because those are the same angles in spherical coordinates. And m sub l could be any integer. It could also be a negative integer, though. And so that was a possibility. Okay. And then we looked at what was left once we did that. Okay. And this was all this great math that we went through. Okay. M sub l there up in the upper left corner, set equal to everything that was left. On Monday, we focused on the things that weren't in the red box, because notice the only variable there is theta, and the only function there was f. And we solved for what f had to be by bringing all the things that were only a function of theta and f to the left-hand side of the equation, and things that were a function of r, the function r, and the variable little r, we moved to the right-hand side. Just pushed symbols around the page, literally algebra. That's all we did. And of course, we made the same mathematical postulate. The only math functions that can solve this mess were constants again. And the constant we chose was this odd thing, L times L plus 1. The other separation constant was m sub l squared with a negative sign, because it worked. And now we've got something that's almost L squared. It's L squared, would be like 4 times 5, as opposed to 4 squared would be a particular example. Okay, so we set that equal to, we set the two sides of the equation after we separated out variables to opposite sides of the equal sign equal to this constant. We worked the first equation on the left there in blue. We worked it and we figured out what the functions are that solved it. Actually, we didn't. We just pointed to a famous mathematician named Legendre who did solve that differential equation, and the solutions take his name. They're called Legendre differential equations. In fact, associated Legendre functions, because it's the associated Legendre equation. By the way, those of you who take advanced electricity and magnetism next semester, you'll come up with Laplace's equation, and oddly, often in spherical coordinates, the solutions to that were also solved by Legendre, and they're just regular Legendre polynomials, and you'll see that. A lot of famous mathematicians, Bessel's another one, right? You've heard of Bessel functions. Oddly, they're the solutions to Bessel's differential equation. And so I guess that's how you became famous as a mathematician in the 1800s. You solved a differential equation with a series of functions. The differential equation and the series of functions took your name. Go figure. Laplace, he also has a set of functions too, but it's for a completely different purpose in differential equations in engineering. All right, in any event, but what we're going to work today, though, is the other side of the equation, which was in red here, okay, the right side of the equation. And so I just rewrote it, set it equal to the same separation constant, L plus 1, manipulated it a little bit, and that is Laguerre's differential equation, okay? And that's, I think, where we left off on Monday. All right, radial equation, Laguerre's differential equation, angular equation, Legendre's differential equation. We've now separated the things out. Remember what the solutions were to the angular differential equation from Monday, associated Legendre functions. All these guys, and something that is tabulated in a math table. And these programs like Symbolab and Wolfram Alpha, they know these functions. And see the nomenclature. We're saying that the solution to the differential equation is the function f, and that is a Legendre polynomial, and it actually should be cosine of theta, and I didn't fix that. And you can see the index L from the separation constant and the index M sub L from the separation constant that got us the G function. They're the indices that Legendre used to specify all of the polynomials in the series. And if you just look at the thing, you'll notice that the upper number can never be greater than the lower number. So we reach the conclusion from Legendre's work that M sub L must be less than or equal to what the value of L is. And I should point out that this angular equation that we worked on Monday, it actually is a differential equation that has an infinite number of different forms, right? Because L right there can be any number from 0 to 1 to 2 to 3 to 4 up to infinity. There's an infinite number of differential equations that are Legendre's associated differential equation. And Legendre just, how many do I have listed here? 1, 2, 3, 4, 5, about a dozen of them, maybe 15 of them. Those are just the solution to the first 15. You can see why this is somebody's life's work. At some point he stopped and other mathematicians picked it up. Okay, and for every L, there's a couple of different values of M sub L too. So you can see this equation here, Legendre's differential equation. Well, it's not just one equation, it's an infinite number of equations. And we just listed some of the solutions to them. Now, what's tabulated? Okay, well, we already know what G is because we solved that before Thanksgiving break. And Legendre gives us the answer to what F is. And there is this math function that people kind of like and have also tabulated, which is the product of the Legendre, associated Legendre polynomials and the solution for G. And you can see that's what's in the table in the blue box. Okay, all that we've done then is we've taken the associated Legendre polynomials, we multiplied them by G, which remember was e to the I M sub L times phi, and then somebody normalized it. And so you can see all the normalization constants done for you. Okay, and that's what we talked about on Monday. All right, let's move on then to Laguerre's polynomial, Laguerre's differential equation, and Laguerre polynomials. And I want to go through, unfortunately, a little bit of tedious math for you. I want to take it, and as I said, much like Legendre's differential equation, Laguerre's differential equation has an infinite number of different forms too, because again, L right there could be 0, 1, 2, 3, up to infinity. It's just an integer. Okay, that's all we're saying. And so you would have an infinite different number of forms. The one that we would expect might give us the easiest function would perhaps be L equals 0. And so that's why we're going to home in on that. Okay. And I think we decided from the associated Legendre polynomials that if L was equal to 0, down in the lower indice right here, well, M sub L could only be equal to 0 as well, because there is no such thing as an associated Legendre polynomial where L is equal to 0 and M sub L is equal to 1. It just does not exist. And so the interrelationship between these constants turns out to come from the solutions to the differential equations. And at this point, since we haven't actually solved them, and that's for another day in another course, we just have to recognize the relationship between these constants. Well, they just have to be rules such that we're learning right now. That is that M sub L has to be less than or equal to L. And so if I decide to go after the easiest, lowest ground state wave function, it's going to be L equals 0, and M sub L will have to be 0 as well. And so that's why I dropped, when I wrote this thing, from this thing, you can see, well, if L is equal to 0, that guy completely goes away, and it simplifies out a little bit. It's an easier form of Laguerre's differential equation. It is conventional, but I'm not going to follow that convention. Some people like to write that first term use the product rule and get two terms out of it, right? And you can do that if you like it. It's style and preference. I'm going to stay with the top one, but I should just point out that a lot of people will write Laguerre's equation, the associated Laguerre differential equation, in the form that's at the bottom. And since we are still doing the hydrogen atom here, the potential energy that we're going to use is the potential energy function that you should recall from your second physics course, your electricity and magnetism course. We might have used the symbol U, right? But it's K, Coulomb's constant, times the product of the two charges divided by the separation between the two. Okay, instead of K, I'm writing 1 over 4 pi epsilon 0. The proton is a positive charge. The electron is a negative charge right there. And so it's an attractive force. So we make it negative. That negative sign and that negative sign cancel. And that's why I wrote a positive sign right there for the potential energy. And that's where the potential energy comes into the hydrogen atom problem. It's after we've separated variables into an R and a theta and a phi differential equation. So we're actually solving three differential equations. The potential energy function, because of the way physics works, it finds itself in the R differential equation, which is what we're doing now, the associated Laguerre differential equation and the polynomials at our solution. All right, so I'm going to just guess at a solution, because although it's heresy and your differential equations teacher next semester will probably bristle if you ever say something like this to them, that is at the end of the day how we solve differential equations. They're very educated guesses, but it's a guess. And so here's going to be my guess. I'm going to say, let's assume that the radial solution to Schrodinger's wave equation is a decaying exponential. Let's see if it works. And that's the deal. All right, so I've given myself some space here to work that. And let's get up what the form that I liked for associated Laguerre's polynomial. That's the one that just has 1 over r squared. And I'm hitting my screen a little bit. That's why my pen stops working. So if I just set things up better, my penmanship will actually be better. 1 over r squared. And then it was the derivative with respect to r. And I'm still writing them as partial derivatives, even though, right, I've isolated the Schrodinger's wave equation into three separate differential equations. At this point, they're not partial derivatives anymore because r is only a function of little r. Okay, so I'm probably being a little bit, since I got in the habit of writing partial derivatives, I'm going to continue to do it. But the mechanics of taking the derivative, whether it's a partial derivative or a regular derivative, is exactly the same. So that was the first term, which I said you could split into two. I'm just not going to. Okay, and the second term is plus twice the reduced mass. Come on, pen. The reduced mass over h bar squared times the total energy minus the potential energy times r equal to 0. That's Laguerre's polynomial, associated Laguerre's polynomial, for the case L is equal to 0, and then M sub L also has to be equal to 0. And I said, let's make our guess be equal to, that R is equal to some constant, and we could normalize to get that constant. With a decaying exponential, this A0 is just some length because the units on an exponential have to be dimensionless. And so if I'm making it decay with distance, I need a constant that makes the exponent be dimensionless. All right, well, I guess that's the deal. So I need this thing right there. So I better take the derivative of r with respect to r. And the good news is exponentials are fairly straightforward derivatives. I just e to the u and then du, which is minus 1 over a0, right? That's that derivative. And then you notice the next thing I have to do is I'm working out here is I got to multiply it by r squared. So I've got r squared times the derivative of r with respect to r is equal to, I'll put the constants together with the negative sign. And then I guess I got r squared e to the minus r over a0. And that's the derivative then that I have to have to do, which is a pain because it's a product rule, right? I've got two things multiplied together here, which are both a function of r. And so when I take the derivative with respect to, I'll scroll up a little bit here so I can give myself some room. The derivative with respect to r of r squared times the derivative of the function r with respect to r, it's going to be the constants. Oops, that's not the one that has the zero. That's the one that has the zero. And I went first times the derivative of the second. Well, I've already taken that derivative once, so I can do that pretty quick with a minus 1 over a 0, right? And then it's plus the second times the derivative of the first, which is just 2r. Okay, everybody good with that? All right, well, before I go multiplying by 1 over r squared, which will be the next step, I guess, I might simplify this a little bit. I got that in both terms. And so it might be, and then I'm going to put the constants together because I got an A0 and an A0 there. So it might be handy to write this as now plus AE to the minus R over A0. That takes care of that guy and that guy and that guy. And then what do I have left? Okay, I think I have R squared over, I got the minus, so that should be plus A0 squared, and then minus the 2R over A0. Okay, all that was the work to get to something I can check with that thing right there, the first term in the Laguerre's differential equation. All right, and so I think maybe it's time now to substitute that solution in. And so I guess what I have is AE to the minus, oh, you know what? There's a reason I factored that out, isn't there? That's my guess of a solution. So really this is multiplied by the guess of my solution, R, isn't it? So I don't have to write this. I can just write it as capital R because it is my solution guess. It is R then times what's left, R squared over A0 squared minus 2R over A0. That's the first term, right? That's that guy. And I did divide by 1 over R squared, hopefully, when I wrote that. Did I divide? Not yet. So I better do that right now because there's a 1 over R squared out in front of it. Okay. And then the second term, 2 mu h bar squared. And I guess I'll write, I'll put in for the potential energy what it needs to be. Okay, so it'll be 2 mu over h bar squared, and that's E, remember it becomes a plus sign, E squared with a K, 4 pi epsilon 0, and an R right there. And all of that is also multiplied by R, and that has to be equal to 0. Okay, need to do a little bit of algebra here because I need to multiply by 1 over R squared in that first term because I haven't done it yet. And I think what I want to do is I want to bring out the complete function for just a second, that guy and that guy. And let's see, the first term will be 1 over A0 squared minus 2 over A0R when I distribute this guy back that way. And then I'll have plus 2 mu, 2 times the reduced mass, over h bar squared, plus E squared over 4 pi epsilon 0 R. All right, all that has to be equal to 0. Well, how's that going to work out? Let's see. I think the entire thing in square brackets has to be equal to 0, doesn't it? But if you look, it's got R in 2 places. Two of the terms are just constants, right? Right there. And two of the terms, even though I've gotten a little messy here, let me clean that up so it's A0R. Two of the terms, this one and this one, have 1 over R, don't they? So let's just manipulate that a little bit so that I put the two things which are constants together. 1 over A0 squared, and then plus 2 reduced mass energy over h bar squared. And then the two terms that are multiplied by 1 over r. Okay, the two that I put the two underlines on, and I'll put them in the better order. Let's see, it's 2 reduced mass, don't forget to distribute, right, times e squared over 4 pi epsilon 0 h bar squared. And then the reason I wrote that one first is because the other one is subtracted off, minus 2 over A0R. All that is multiplied by the function itself, and it has to be 0. Well, again, now I think separately then, this thing has to be equal to 0, and this thing has to be 0. It's sort of like saying, if I have a polynomial, a0 plus a1 times x plus a2 times x squared is all equal to 0. What I'm saying is that the easiest way to do that is to require all the coefficients, a0, a1, and a2, the coefficients of the individual powers of x. If they're all equal to 0, well, then you can guarantee that you've got 0. Okay, and so that's what we're saying here. That's why this is all multiplied by, oh, come on. This is all multiplied by 1 over r to the 0 power, right? This is all multiplied by 1 over r to the first power. If those things are separately 0, well, then certainly that'll solve the differential equation for me. All right, well, let's see what that implies, because that's really the deal here. What does that mean? I think it means, in the first case, 1 over a0 squared plus 2 u times the energy over h bar squared is equal to 0. That tells me that the energy here is equal to, solve for it, minus h bar squared over 2 reduced mass times a0 squared. Like, that's what that tells me. It tells me what the energy is. And remember, this was for what we believed would be the lowest energy state. Okay, we're going to give that a name here in a second. But now I guess the question still is, what's this A0 thing? If you look at the second term right there, okay, 2 mu e squared over 4 pi epsilon 0 h bar squared minus 2 over A0. There should not be an R right there, should there? I factored that guy out. It's already right there. I don't know why I wrote it again. It shouldn't be here either when I tried to catch it. Okay. And but in any event, I suppose that we said has to be equal to 0 as well. Solve for A0 here. And that tells me that A0 is, the twos cancel, don't they? Okay, A0 would just be equal to the reciprocal of all of the first term. So A0 is equal to 4 pi epsilon 0 h bar squared over the reduced mass. That's not a mu 0. That's the permeability of free space. Just the reduced mass times the charge on either the proton or the electron squared. That thing had a name back a couple weeks ago. That was called the Bohr radius, wasn't it? And so out of Schrodinger's wave equation, in spherical coordinates, 3 dimensions, when we got to the R differential equation, the answer for the lowest energy state that we could possibly imagine, the lowest, to solve for the lowest wave function, then we managed to recover with a guess of a solution, Bohr's radius. And then, of course, if you put that right into there, what you get, and I'm going to leave the math for you, I guess, is, and I'm getting rid of 1 over 4 pi epsilon 0. I'm going to call it just k squared, e to the fourth reduced mass over 2 h bar squared, which was the Bohr energy back when we were looking at the Bohr model. And so Schrodinger's equation in spherical coordinates is completely consistent with that. All right, that's the fun math. Great. What about other solutions? And oh yeah, this is the lowest. This is the lowest case, the lowest wave state, the lowest energy. We're going to use the nomenclature that Bohr came up with. That we're going to call the n equals 1 case. Now, I'm not going to solve or even guess at all the other solutions to all the other variations of the associated Laguerre differential equation. I'm just going to tell you, Laguerre solved them. Another blue box here, and there they are. Okay, and you can see there is the lowest one that I just was playing with. Okay, and somebody even did us a service. It looks like they may have even normalized it for us. So that was kind of nice. Okay, but that's the solution we worked out, and that would give us the lowest energy. When you move up to the next possibility, I guess we're still doing L equals 0, there is another solution that works. In fact, it gives the next energy level up. You can still stay with L equals 0. There's a third solution, and it probably wouldn't surprise you that for L equals 0, there's a fourth solution as well. And so there's a large number of solutions when L is equal to 0, which has consequences for what the angular wave function looks like. Okay, and each of them has a different energy state. The lowest one being what we call the n equals 1. Okay, there is a relationship in these things between the energy state that you get and what the index n and l should be. And you'll notice that for a particular value of n, once Laguerre works out all these polynomials, l has to be less by 1 than the value of n. So notice when n is equal to 1, you can only have L equals 0. When n is equal to 2, you can have L equals 0 or 1. When n is equal to 3, you can have L equals 0, 1, or 2. And that's it. And you can guess what 4 would be: 0, 1, 2, 3, for n equals 4. And we just haven't listed those on the table. The subscripts on R specify the values of n and L. N being what's the wave state's energy, and L being related to the to the angular solution and the Legendre polynomial, the associated Legendre polynomial that we showed before. I'll get you some pretty pictures here because I got to do that. But first, I want to talk about what the pictures represent. Probability distributions, the probability that you're going to find the electron somewhere in the region of space around the nucleus, which is just a proton. And so remember when we did one-dimensional problems, we said that probability in a particular region of space, in one dimension, it was dx. In 3 dimensions, it's a volume element. I'm going to use the symbol tau for volume element because we've already used V for potential energy, right? And you'll see that that's a common upper level physics choice. In spherical coordinates, though, it is just exactly what hopefully your multivariable calculus told you: r squared sine theta dr d theta d phi, right? That's what I mean by d tau here, same as dv. If we integrate that over all space, that's all values of theta from 0 North Pole to South Pole pi, phi from 0 all the way around to 2 pi, okay, and r from 0 to infinity. When we do that integral, we got to get 1. That's our normalization condition here. Hopefully that makes sense, consistent with what we did in one dimension. I've written that out for you here. If we're only interested in the probability distribution in the r direction, Well, you can just do the theta integral right here, again from 0 to pi, North Pole to South Pole, and you can do the phi integral right here, okay? And that's 0 all the way around 2 pi, like longitude, if you will. And what we're looking at then for the R probability distribution, that R squared from the volume element finds its way into the probability distribution for the coordinate R, moving away from the center of where the nucleus is. And so the radial probability density then is R squared times the function that we just found, the associated Laguerre polynomial squared. Picture time. Here's some probability distributions for some of the simpler ones. We just did the case 1, 0 right here, the decaying exponential. That's what the function R looks like. The probability distribution then, which is R squared, little r squared, times big R squared, looks like that for the simplest case. And then you can see as we move up, because of the R squared here, you get little humps on what are otherwise simpler wave functions. And these were just the wave function R listed in the table. This over here is R squared times that wave function, the radial portion of the wave function squared. And you can see there's the next one up for n equals 3. And so I think the pattern here is this is n equals 1. This is what n equals 2 looks like, because you can see the first subscript is 2. This is what the n equals 3 looks like. Okay, it's radially away, but now you have to, in your mind's eye, combine that with the spherical harmonics as well, right? And what you have then, remember our picture for what the spherical harmonics looked like the other day were these things, the 0, 0 case. And remember, the subscripts here are L, M sub L, okay? L, M sub L, excuse me. Okay, and those were the first couple that we showed from the table, what they look like in 3 dimensions. And now if you're trying to get the entire wave function, I'll come right back to this in a second, okay, you've got to go and you got to look at, okay, what are the Legendre polynomials look like in 3 dimensions? What do the Laguerre polynomials look like as you move out radially? And you got to try to graph them. And I'll give you a little bit of an example for 1 or 2 of these of where they come from. There's more pretty pictures of this thing. Let's look at what we just had. Okay, it took a second there for that thing to show up on my PowerPoint. Let's look at this donut thing right here, which you'll notice is the 2, 1, plus or minus 1 case. And so what is that a combination of? That is a combination of the 1, L equals 1, M sub L plus or minus 1. That's that guy, right? But superimposed on it in the radial direction is the n equals 2, L equals 1 case, which is that guy right there, which I think is the dashed line. And so this donut, which is shaped like that, all of a sudden there's a most probable place where you're going to find it. Okay, the most probable place is right there, and that corresponds to right in the middle of that thing right there. And so we've kind of taken the donut from the spherical solution, the angular part of the spherical solution, and we've given it a most probable radial distance. That one's pretty easy to kind of deal with. Let's look at the next one then. And again, we'll start with the spherical harmonic, L equals 1, M sub L equals 0. And that would be, let's change colors here just to keep it a little less confusing. That would be this guy, wouldn't it? Okay. And then on top of that, we're putting 3, 1, which is this guy right here, the dashed line. Notice it has kind of 2 humps. And if you combine these 2 together, apparently you get that shape. I have a little trouble visualizing that one, but I can see the pieces here. There's a kind of a radius right there where there's a high probability that would correspond, I think, to the first hump. And then the second hump right here corresponds to the second guy looking downward where you have a probability in the angular case, and you have the same thing going upwards. It's just a little harder to see because that kind of mushroom looking shape is being obscured. All right. If you're following me there, I hope that it makes sense that I got the 2-0 right here. That's this guy. Maybe I should change colors again. That's this guy right here. Okay. And it's combined with 3-2. Where's 3-2? 3-2 is the dashed line right here. Okay. And so those two come together and give you that shape. And that's probably legitimately believable as well. All right. And so that's how these wave functions come together. And if you've taken a chemistry class, why is this important? Well, we're just doing the hydrogen atom right here, but you can do this for more complicated atoms too. It's just a whole lot harder. You generally do it with numerical techniques, and that's where the electron is hanging out in order for it to bond with an adjacent atom. And so you see these kind of diagrams when we're talking about atomic bonding. All right. Let's see if there's anything else. Yeah, more pictures. I would recommend going to dogger.com, except I found out they charge apparently to see some of their pictures as well. All right, I got just a couple more minutes then. I want to come back right to here and restate the rules that came about from the solutions to Legendre's associated differential equation and Laguerre's associated differential equation, and just state them on one page. And that is, once you've decided what the energy state is, and you've decided the lowest one, the next one up, etc., you define what one is, what n is, because n, just like in the Bohr model, is the number that is associated with the energy. How is that associated? Let me find that slide, which I think I blew by too. Where did I put it? Oh, there it is. Yeah. The principal quantum number n. Remember, all of this was what we just got from the solution to the radial equation with my guess. And then just like the Bohr model, we say any other energy, that's the n equals 1 case. Any other, you just divide by n squared. Okay, great. So once we've got that, we decided, or more correctly, Legendre decided that for the series of polynomials, L could only be an integer starting at 0 and could only go up to 1 less than n. And actually, it's Laguerre that decided this, not Legendre. What Legendre decided is that m sub L in his polynomial series could only range from minus L to plus L. And so these are the restrictions on the quantum numbers. Works out of the math. Someday when you get a chance to solve the math of these guys, it'll hopefully make a whole lot more sense. I'm already over here, I just noticed, by a couple minutes. I do want to transition over to a worksheet real quick. Nope, I'm not going to do that. I'm just going to, we'll go back to what I was just talking about. I want to make the point, I guess, of what would be the wave function if we had a set of quantum numbers. And let's see, stop that. If I had a set of quantum numbers, let's see, n equals 2, so it's the second energy level. Let's see, L equals 1 and m sub L equal to 0. What would the wave function look like? Okay, well, we have to go put that all together from those two charts that we had. We're now looking for the wave function. And let's see, it's going to be, let's start right here. We said L equal to 0, m sub L equal 1. So I guess I need that thing, 1/2 square root of 3 over pi cosine of theta. So that's going to be what my wave function is, at least for the angular portion. 1/2 square root of 3 over pi cosine of theta. That's the spherical harmonic part. Why? Well, now we just looked at the radial portion today. These two guys, 2 and 1, are the way I get the radial portion. So I got to find a radial chart here. And I've already scratched all up on it. Let's get rid of all that stuff real quick so I can point exactly what I'm looking for. We said n equals 2, L equals 1. N equals 2, L equals 1 is that line right there, R over A0. E to the minus R over 2A0, square root of 3, and then the constant 2 over A0 to the 3 halves. And so that would be the rest of the wave function then using these charts. And so I guess I need R right here, which is what I just said, 1 over, try to get it in the same order I read it off, A0 square root of 3, and then there was that 2A0 to A0, and that was to the 3 halves power. And then I need in the numerator R times e to the minus R over 2A0. And so that would be my wave function, right? For this particular series of quantum numbers. And you can see you can build any wave function that you want. And then what we've endeavored to do, I guess, in the pictures I showed you is plot what does the probability then look like, psi star psi, in 3 dimensions. And that's what the pictures represent. Now, there is one more point I guess I want to make, and then we're done. Although I've gone at least 10 minutes late here. If you have to go because you got another class, this will just take a second, but if you got to bail out, go right ahead. I want to look at all the possible quantum numbers that could be associated with the n equals 4 energy level, right? What we've been calling E4 when we were doing the Bohr model, using these rules on this slide. Okay, so the first one I can have is 4, and I don't need a parentheses right there. I can have a 4, I can have an L equals 0, and I can have an M sub L equals 0, right? Then I can have a 4, L equals 1, M sub L is equal to minus 1, 4, L equals 1, M sub L is equal to 0, 4, M equals 1, M sub L equals plus 1. So there's another series of quantum numbers, all which would have the same energy, E4. Well, we can keep going here. You can see, and I'm going to start writing smaller. I can have 4, I can have L equals 2, M sub L equals minus 2, 4, 2 minus 1, L is equal to minus 1, 4, 2, L equals, M sub L is equal to 0, 4, 2, 1, and 4, 2, 2. There's a series of wave states, wave functions, which have the same energy, E4. Okay, and last one here, I better make a little more room for myself. And that would be, okay, n equals 4. L can be as big as 3, so we're done now. There's no higher value of L, but the allowed values of M sub L are minus 3, minus 2, minus 1, 0, 1, 2, 3. I could just go ditto signs here all the way down, but we'll write them out. And that's the last set of quantum numbers that all have the same energy because they all have the same value of n equals 4. And I want to count them out. How many do I have here? 1, 2, 3, 4, 5, 6, 7. 7 of those guys. 5 of those guys. That's 12. 3 more. 12 through 15, and 1 more, 16. There are a total of 16 different wave functions, all that would have the same energy, which is the first energy, the lowest energy state, divided by, in this case, 4 squared. What do we call different wave functions that have the same energy? We said they were degenerate. So the degeneracy of the n equals 4 state for an electron moving around the hydrogen is 16-fold there are 16 different wave functions that can all be constructed exactly like I did for this case over here. That was a n=3 case though, wasn't it? Okay, n=2 case. There are 16 different wave functions that would all have the same energy, E4. That's it. And there would be 16 different shapes that you might draw in a mathematical problem. And that's all I got. That actually is the 34th worksheet. I just worked through the two problems on it right there. I appreciate your patience. Let me go over here. I'll stop sharing this real quick and tell you, I wish you all the best of luck moving forward. I hope a number of you decide to major in physics because every one of you has the ability to handle that, I'm sure. And it's been a lot of fun working with you all through the course of the semester. One more event next week and you're done with me. And I wish you the best of luck for you rising sophomores. I do hope you get the chance to take the quantum mechanics class in your first year, your senior year. And I guess, yeah, as the freshman, you could take it in your junior year. I think it'll be a great addition to your understanding of this. Wish we had another semester to continue on with the hydrogen atom, but heck, I've already gone 13 minutes past my time on the last day of class as it is. So best of luck to you all. Do well on the exam. Everybody keep your A or maybe a high B in one or two cases, but I think everybody could wind up getting A's here. That's what I'd love to put into the grade program at the end of next week. Any questions for me? All right, again, apologize for keeping you long on the last day, a little long-winded. I'm going to stop